Okay, so I'm going to try and wrap up this sketch of the proof of H-coordism theorem, and we boiled it down to the following situation. Step. So we're in, the coordism is n-dimensional, so it's like n-dimensional. But we're now working inside a regular level set in n minus 1 manifold. So we're in some n minus 1, okay, which is simply connected. Actually, maybe before I go on, I'll talk about, well, let me set this up and let me talk about the simply connected thing, because that's something I also kind of flubbed last time, didn't quite say it the right way. So this is a regular level set. Then we have two critical points that we're trying to eliminate two flow lines between them. Okay, so we have an ascending manifold for one critical point, which, so there's a, we've got a descending manifold for a critical point above, and that's index k minus 1. That's index k. Let me just. Yeah, I'll call it, it's a k minus 1 manifold. It's actually a sphere. Okay. I mean, really, this is the sphere. I've got the descending disk, descending ball, and then intersected with this level set. We'll call that a sphere. So that's the sphere of k minus 1. Then we've got the ascending manifold, which we've got the ascending disk, which is n minus k minus 1 dimensional. Okay, and then I subtract 1 from that, right? And so I get n minus k. That's this k sphere. And then I've zeroed in on, now I've got the 2 points of intersection. I've got points, what did I call them last time? P plus and P minus. P plus and P minus. Points of the intersection of D intersecting with A. And they're plus and minus because they occur with the opposite sign. And I'm going to choose a path, let's say, choose a loop, gamma, in D union A, which is made up of a path from, let's say, gamma minus to gamma plus in D.
P minus to P plus.
P minus to P plus, followed by from P plus to P minus in A. And then the goal, we want to sort of say that the picture looks like this. Which one do I want to move? I think I drew it the other way around, but it's sort of more natural to think of isotopping the descending thing. So, I'll still, they're equivalent, right? So I see a little piece of the ascending sphere. I see 2 points, P plus and P minus. Then I see this curve, the part that's in the ascending sphere first. And I see this other part that's in what maybe I'll call this path gamma D. A. This is gamma A. This is gamma D. And then I'm not going to, well, gamma D is part of D, but I'm not drawing all of D because I want to emphasize that D intersect A is just 2 points. So if I try, I don't have enough dimensions to have 2 surfaces intersecting in 2 points here. So I'll draw, and anyway, this A is, 27 dimensional and D is 95 dimensional, right? Whatever it is, they're intersecting at 2 points, and but I'm just drawing. In any case, I'm just drawing parts of each, right? I'm just drawing some slice. What we really want to do is say that we're going to set up a model for this piece of the intersection that's actually inside a 3-dimensional ball, and then next thing we're going to say is we're going to find a disk. That was why D was a bad choice. So, but anyway, we can find some disk Q. Okay, so we find an embedded disk Q is going to be embedded in the complement of m minus d union a, well, except for the boundary. Put it this way: embedded disk Q would be except for the boundary. It really should be transverse. There's sort of this nice transverse model you want to set up. And so in the interior of Q, I don't want to see A or D, right? And then I'm going to say, well, then there's this nice ball inside M, a nice three-dimensional ball inside M, along which I can do the obvious thing. So then, put this in D3 inside M. So it looks like this. Everything just exactly like that, and then do the obvious isotopy, which you can either think of pulling gamma down or moving A up, either way. But the point is, you'll do an isotopy in this ball, and then you should have a collar neighborhood of the isotopy. Well, you should have a product. It should be really what should be going on is just this cross something appropriately, right? And so that I can say, well, just move A up and over, and well, A is really higher dimensional, it's not just two-dimensional, okay? But I move it up and over, and then in the other directions, I use a bump function to sort of damp that out so that outside the neighborhood of B, I'm not doing anything. And so that's our task, is to try and make that as rigorous as we feel up to making it. Okay? And that will eliminate those 2 points. But before I get there, I should talk about this simply connected. We know that X is simply connected, and we know that the bottom and the top are simply connected. And we know that, so Y, regular level sets. Connected. Okay. So the point is this: we have. So what do we have? We know m0, pi 1 to 0 equals 1, pi 1 to x equals 1, and no 1 or n minus 1 levels. Okay. So so each, we just work from the bottom up, okay, and argue that we're not going to create any fundamental group. We know that we're not creating any fundamental group for X ever, but as you can see with 3 manifolds and a 4 manifold, even if you create no fundamental group for the 4 manifold, you can create fundamental group on the 3 manifold slices, because when you add a 2 handle to B4, for example, the boundary B4 is S3, you can add a 2 handle that changes the boundary manifold by surgery. We know you can get any 3 manifold that way. In particular, you can get arbitrarily, you can get 3 manifolds that are not S3, which is all other 3 manifolds that are all non-simplicated 3 manifolds. So we have to be careful. But why? So what we need to do is need to show that the surgeries involve, the surgeries on the n-1 manifolds at each level never produce pi 1, right? Well, why would surgery produce pi 1? What is surgery? So the surgery we're doing is you take going from one, we just do it inductively, right? So we're at, say, one level set is simply connected. We want to show moving above the next handle, but still simply connected. So we take, say, n-1, we remove some solid torus, so that's an S k minus 1 cross a b n minus, we want the total dimensions of b n minus k, so the total dimension is that. right? And then we glue in something, right? Union something else. Union what? Union A, B, K, cross S. Now what is K here? K is between, K is bigger than 1, right? K is between 2 and n minus 2, right? And n is as big as we want it to be, right? We'll see what we need for n. We know that if n equals 3, well, what am I doing here? That's right, so this doesn't even make sense anymore. Sorry, if n equals 4, right, then, no, this does make sense in the case of n equals 4, and we know that when n equals 4, we don't expect this to work, right? We know that if n equals 4, then we're doing surgery on 3 manifolds. There's only one k that's possible here, which is k equals 2, and that's the normal surgery on 3 manifolds. We know that that can produce pi 1. So, well, okay, so how do you produce pi 1? Well, you know, as my read torus, first you remove this, and then this could have pi 1, or this thing could have pi 1. Well, this thing's never going to have pi 1 unless n minus k minus 1 equals 1, right? So we want n minus k minus 1 to be bigger than 1, which means n minus k is bigger than 2, which means n minus 2 is bigger than k. And so, okay, so conceivably when we glue this thing in, right, we'll look at the case, let's save the case, k equals n minus 2 terminate. So that's for the moment. So for now, let's assume k is less than n minus 2. Okay. Therefore, pi 1 of the part we're gluing in is trivial, right? But still, we might conceivably have some pi 1 here, right? Which is not, I mean, we glue this in with trivial pi 1, that doesn't mean that, just because we're gluing something in with trivial pi 1, that doesn't mean it kills whatever pi 1 we had by drilling something out. So then we have to think, what about pi 1 of this? So when we glue, so the idea is, you know, think about a 3 manifold. How do you get pi 1 when you remove a solid torus, right? The reason you get pi 1 is because there are linking circles. So there are disks in a 3 manifold which cannot be made disjoint from the S1 that you're removing. Okay? So the reason you would get pi 1 is if this SK minus 1 intersects a D2 non-trivial at a point. Okay? You got that? So if, in other words, if I'm in a 3 manifold, I carve out a circle. I mean, really thickening it up is, we're just doing fundamental groups, so who cares about whether you're thickening it up or not. If you carve out a circle, remove something, why could you get a non-trivial loop? You get a non-trivial loop that goes, you know, something that used to bound a disk and no longer does. So you've got to puncture that disk. Okay? So, so what about pi 1? So to think about pi 1 of this piece, we want to make sure, to make that always be trivial, we want to make sure that the SK minus 1, we want that should generically miss disks, right? In other words, if you make things transverse, and if you had a disk that killed some loop, it should still kill that loop after you glue it. Well then, this is just this D2. So in other words, we want to make sure that K is such that inside an n minus 1 manifold, a K minus 1 manifold and then 2 manifold are disjoint. Okay, so how do we do that? Let's see. So let's calculate the intersection. Let's calculate the dimension of the intersection, of the transverse intersection of a K minus 1 manifold and a 2 manifold in an n minus 1 manifold. So we just go through the same thing. I add codimensions. So this has codimension equal to n minus 1 minus k minus 1, which is n minus k. Okay? And then this has codimension n minus 3. Okay, we add the codimensions, right? So the sum of the codimensions is 2n minus k minus 3. Okay, what do we want? We want that to be big. What do we want that to be? Big or small, first of all? Well, let's go to therefore the dimension of the intersection, right? Dimension of the intersection that's the codimension of the intersection. So the dimension of the intersection is n minus that. So that's n minus, so that's going to be k plus 3 minus n. So we take n minus that, right? And we want that to be negative, right? In order for there to be nothing there. We want that to be less than 0. So we want n to be bigger than, we want k to be less than n minus 3. Did I do any calculations there? Wrong?
Should be n minus 1 minus.
What did I do here?
We're doing this in n, right?
Say it again?
We're doing this in n, so it should have been n minus 1 minus.
Oh, yeah, right. That's where things got off. Sorry. Okay. I added the codimension was good so far, right? This is the last step. So I want to do n minus 1 minus 2n minus k minus 3. Right? So now, what is that? So I've still got k, I've got a k plus 3 minus 1, so that's k plus 2 minus n. We want that to be negative. So again, we want the same thing. N needs to be less than k minus n. K needs to be less than n minus 2, which is the same thing we had before. Okay? So those two conditions. So really it's the k equals n minus 2 situation that comes. Yes?
I'm slightly confused by something you said before. So M is simply connected.
Yes. I'm doing this inductively. So n0
Sure.
is simply connected.
So
yeah.
if you take a simply connected manifold and you dig out, I mean certainly if you take a simply connected 3 manifold
Yeah.
and you dig out a solid torus,
Which is the same as digging out a circle in terms of
Sure.
Okay.
So then you do know that if you glue something back in with trivial fundamental group, then you're going to get something simply connected, right? Because I don't understand. I don't understand that statement.
Oh,
of
I
like,
see. What did I say? What did I say?
You said
Yeah,
that-
right. Sorry, if it's got trivial, yeah, I said something dumb. You're right.
But you need, I mean, as long as what you started with is simply connected, no matter what you cut out, if you glue something back in with
Right.
trivial fundamental group.
You're right. So, yeah, I said something dumb. So I did an extra calculation.
But I guess it makes
Same
sense that
answer.
you got the same answer.
Yeah, right. Yeah, I said something dumb. I was thinking of the 3-manifold case where you
If
don't
it's not
necessarily kill that
simply
fundamental group, but it's not simply connected.
Yeah,
It's going
right,
back in.
then certainly.
You're absolutely right. I was being stupid about my resource. Right? Right. No, you're confusing me. Right? You can glue two things together. Right? One's not simply connected, one is simply connected, right? And you can produce a non-simply connected piece, right? So if you, maybe, so I just think of this as aiding. I mean, this may be a special case in which there's something more subtle going on, but in general, I just wanted to use Van Kamp's theorem at the crudest level. I've created two pieces I'm gluing together, right? And so it is, I could start with something non-simply connected, remove a ball, and put a ball back in, right? And I don't make it simply connected, even though I put something simply connected in.
Sure,
Right?
that's
So that's not this case, right? But the real point is, that, if you want to be more careful about it, then I was trying to be as crude as that. I've removed something, if that thing's simply connected and this thing is simply connected, then that's all I have to worry about, right? If this thing is not simply connected and this thing is, well, then I have to think about the intersection. The thing I'm gluing along, which is a sphere across a sphere, and make sure I'm killing the right things and so on. But this is as crude as I need to be. Okay. When we get to this case, maybe the n equals 2 case, we might want to be a little more careful. So anyway, that's the same thing. So this is so in that case, we're fine, right? Now, what about the case of k equals n minus 2? Well, we turn things upside down. Okay? Because notice that k equals 2 doesn't cause any problems for us. Right? We want to know that we want to turn things upside down, but we want to turn things upside down and make sure that k equals 2 is not the same as k equals n minus 2. Right? It's always the idea that we want to turn things upside down and actually make progress. Okay, so k equals. I'll just
Maybe as
try to
long
write-
as n is bigger than
as long as
bigger
n
than
is
4.
big, right. As long as n is bigger than 4, then k equals 2 is not the same as k equals n minus 2. So we turn it upside down and we work from the top down. So in other words, what we're saying is you can work from the bottom up all the way up to the very last handles, the last index. And then we don't really have a guarantee that we're not simply connected going that way. But then we know that the top is simply connected because the thing is a cobordism. Okay, so the top's got to be simply connected. And so we work from the top down, and those are index 2, which is not the same as n minus 2. And so we're going to get simply connected working from the top down. Okay, so should I write any of that down? And then, so k equals 2 up to n minus 3, pi 1 and it's trivial for all level sets. Level sets. And then if n is bigger than 4, so that k minus n minus 2 is greater than 2, then turn upside down. Right? And turn it upside down and work. N minus 2 becomes 2. I should have missed that, but you understand. So now we finally let's try and say that carefully. So that's why all the level sets are connected. Are simply connected. So what do we want? So 1, 4. I've got A and D embedded in M. And minus 1. Just erase the most important thing. The ascending manifold is n minus k dimensional. Right? And the descending manifold is k minus 1 inside there. Those are both spheres. And then I've got p plus and p minus, gamma plus, gamma minus, gamma A and gamma D. Just one more time, sorry about that. So there's A, there's gamma D, gamma A, and then, so now let's argue about the existence of a disk, okay? So, M is simply connected, so the whole loop gamma is the boundary of some disk Q, but the question is, can I make Q disjoint from everything else? So the first thing I would do is I would push gamma. So this is a local model in which the intersection happens. First thing that's maybe useful, what I really want is pi 1 and M minus A union D. Okay, because what I want to do is push gamma up off of A. So I want to make a little collar neighborhood on gamma. And so I want to do something like that. First build a little annulus that's transverse to A and D where those boundaries meet. And so that's fine just in this local model. That there's no, I take a collar neighborhood of gamma D. I take a two-bit neighborhood of gamma D, and that'll be an arc across a disk of the ball of the appropriate dimension, right? In there, I will see gamma A, being a certain. So I'll see inside gamma D. I can start with gamma D like this. I take a two-bit neighborhood of it, and then gamma will initially hit the edges as just something like that, right? And then I can just pick some interval, some strip in there, use that to push gamma D off of. okay?
You want all this in the level set, right? Or
This is all happening in
All
level
in
set.
level
From
set.
here on out, we're just working in this n minus 1 manifold, okay? So I can push gamma d off of itself and and then also push gamma a up in a way that it joins up, and so that's not really any issue, is to get sort of a gamma prime that's entirely in the complement of a and d, and then connected by an annulus to gamma. Okay, and so then we want gamma, so we get gamma prime with there's an annulus, call this alpha annulus, and then so that the boundary of alpha equals gamma d prime, okay, and then gamma prime is contained in m minus a and d. And now we want to think is hopefully m minus a and d is simply connected. Hopefully our dimensions are high enough, right? Well, again, let's if we want, so what do we want? Well, we sort of already saw it here. In order to have a complement of something be simply connected, maybe I should have done it in full generality, right? If can we just redo this? If I have something, suppose this is just let me redo this here. Suppose this is just dimension L. So I have something of dimension L, which I want to miss disks inside an n minus 1 manifold, right? So this codimension is n minus 1 minus L, okay? And so the sum of those codimensions is n minus 1 minus L plus n minus 3, which is n minus 4 minus L, right? And then the codimension is going to be in this, so n minus 4 minus L, and so now that's going to be L plus 3. Right? Whatever L was. Now all I have to do is redo that calculation for just an arbitrary, this is very nice to see, this is just some L dimensional manifold. So I'm looking at the question, if I have an L dimensional manifold inside inside a simply connected n minus 1 manifold, what is the chance that the complement is simply connected? Okay. So I have these two, I'm going to think of them one by one. So what I need is I need that L needs to be less than n minus 3 for that to work, right? And so, do I have that? Well, in one case I want to need n minus k to be, that's our L, to be less than n minus 3. Cancel, and that means we need k to be bigger than 3. And doesn't go well. Hold on. And so then we also want k minus 1 to be less than n minus 3. So that means we need n to be bigger than, we need k to be less than n minus 2. Okay, so again, in those middle ranges, we're fine, right? For k from 4 up to n minus 3, we won't have any trouble arranging this this disk to be embedded, to be embedded and disjoint. K from 4 up to n minus 3. So now we need to think about k equals 2, 3, and n minus 2. Now, of course, n minus 2 and 2 are going to be the same, right? So if we can do n minus 2, we can do 2. And let's see, why is n minus, why is n minus 3 not showing up? I want to say, I feel like something went wrong in the count because if 3 is a problem, oh no, k equals 3 means I have, oh right. First of all, k equals 2 and n minus 2, what is k? K is the index of the higher critical point, right? So k minus 1 is 1, right? So this never occurs actually, right? Because we already eliminated, we're looking at flow lines from index k down to index k minus 1, right? And we don't have any k minus 1 when k equals 2. So this is, k is not equal to 2. In this case. We do have 2 handles in general, but we're not trying to do this move on it in this case. We're not going to do the move in this case. So k equals 3 and k equals n minus 2 are really the same case. We're looking, k equals 3 is where we have an index k critical point, an index 3 handle, and 2 flow lines down to a 2 handle, and we're trying to cancel those. And n minus 2 is where we have an n minus 2 handle and flowing down. If we turn this upside down, the n minus 2 becomes the 2 handle, and so we have this, these are the same case. Okay? Everyone understand that they're really the same situations, the same case.
But, I mean, A is a sphere. Right?
A is a sphere, yes.
So if K is 3, then that's a codimension 2 sphere in n minus 1 manifold.
Okay, so you want to wonder whether
this
is actually a problem at all. Well, it may be.
No, I think that means it might be a problem, right? Because it might be not a.
Yeah, that's right. So, yeah, I mean, these are non-trivial problems that we have to think about. Okay, in both cases, yeah. I mean, that right. This calculation was not, this calculation does expose one sort of important case we have to think about. But these are the same case, so I'm just going to focus on k equals 3. Right? Because k equals n minus 2, we just flip it upside down. And, I mean, this really involves a 3 handle and a 2 handle. This involves an n minus 2 and an n minus 3 handle. So they're the same case, so we focus on the case of k equals 2. Everything else will work fine. And so in the case of k equals 3, we have the descending sphere is a 2 sphere. D2. Right, now D2 is terrible, so it's an S2 inside this one. Right? And then the ascending manifold is a n minus k, n minus k is a 3 sphere, an n minus 3 sphere. Inside this one manifold, and as you were saying, that's the one that can cause non-trivial fundamental, because that's codimension 2, and that's where knotting can occur. However, so this is the last point that I where is this coming from? This is the ascending. Sphere for a. This is the ascending sphere for a 2 handle, right? We got a 3 handle and a 2 handle involved, right? Now, we've already. So I want to say that in fact, it isn't causing. It isn't not essentially. I want to say that in fact, the fundamental group of the conflict is still trivial, although it could be non-trivial. In our case, it's trivial. That's what I can't just use a dimension argument to say it's non-trivial. Okay. So the point is, we've got some. So how do I see it in the level set above the 2 handles? So here's my index 2 critical point. right below it and right above it. Let's say this is M and this is M prime below it, right? M is above. I've got an index 3 critical point, which is, what I care about is those flow lines. But right now I'm just going to focus on, we know that this S2 is not causing the problem. Okay? It's this thing that might be causing the problem fundamentally. So we want to see where is that n minus 3 sphere inside this n minus 1 manifold. And of course it came, we so go back to thinking about surgery again, right? And so this n minus 3 sphere, we took, so derivative m is m minus, well I attached the index 2 critical point, right? So I took out an S1 in the surgery, m minus S1 cross a ball of dimension n minus 2, so that the total dimension is n minus 1. And then I glued into that the ascending sphere, which is B2 crosses Sn minus 3. And it's this Sn minus 3 that I glued in that might be, whose complement might be simply connected, right? So I want to know, so m minus this Sn minus 3 is really the same thing as, well, I'm going to write this down. I think it's just the same thing as up to some contraction, because if you glue in B2 cross, so you have to think about carefully how B2 cross Sn minus 3 is glued in, right? It's glued in along S1 cross Sn minus 3. So when you remove the S1 cross Bn minus 3, you have an S1 cross Sn minus 3, which is sort of like a solid torus. One direction is S1, the other direction is Sn minus 3, right? And then you glue it in so that as you go around, maybe I'm going to do the other way, S1, Sn minus 3. Okay. As you go around the Sn minus 3 direction, you fill in the each S1 with a ball. Okay? That's what the surgery is. So now, putting that, removing the Sn minus 3 runs right through the middle there. And puncturing that, removing this Sn minus 3, is the same thing as just not putting this in at all. Because, well, maybe I should say this to explain. So let me try to justify that claim. If you take, well, the real point is this: B2 cross Sn minus 3 minus B2 cross minus 0 cross Sn minus 3. What is that? That's diffeomorphic to an interval cross S1 cross Sn minus 3. Right? Because B2 minus 0, a ball minus a point, is an interval across a circle, annulus. Okay? And so, I mean, open, closed, right? Very precise, right? So then, if you glue in B2 cross Sn minus 3 along an S1 cross Sn minus 3 and then remove the core, all you're doing is gluing a collar neighborhood on the boundary. Okay, all you're doing is gluing a collar neighborhood on the boundary, and that doesn't change the fundamental group at all. It doesn't change the manifold, and that's why I claim that it's diffeomorphic to just n minus S1. So if you do surgery and then you remove the core of what you did, is the same as not doing surgery, just attaching a collar neighborhood on the boundary. And since this, we already went through showing that this thing is simply connected, right? Because of the fact how these, well, we know that it has to be simply connected, the whole thing is simply connected. We already know that, again, that's something special about how we're doing this, but we know that phi 1 of m minus the Sn minus 3s is trivial. Therefore, I mean, the S1 cross Bn minus 2s. I mean, we know that an S1 can't create fundamental group in this high enough dimension, right? It's trivial. Therefore, phi 1 of, that's n prime. That's what I, if you confused anybody at all, that should be confirmed. Okay, the lower left. pi 1 of m prime, pi 1 of m minus this Sn minus 3, it's got to be trivial as well. Okay. So, that was the special case that we had to argue a little more carefully, but the whole point was, this is not, these Sn minus 3s are not just any old randomly embedded Sn minus 3s. They're actually the belt spheres of particular two handles, and those two handles don't create any fundamental group when you remove them, so the spheres are embedded so as to not kill the fundamental group. And so, let's see. I think I will skip the details about how, I think you can probably buy, and once you get this embedded disk as a complement, then you can probably figure out for yourself, or there are places where it's written down carefully how to just think about this model. The point is, you take A, union this disk, and the disk Q will intersect, by construction, intersects A transversely, because we started out with a transverse annulus. So we've got A and we've got a half disk, it's really a half disk, right? Meeting it transversely. So therefore, those two things, we can take a 2-bit neighborhood of A, union of 2-bit neighborhood of the half disk Q, and that's a ball, right? And then we, that's just, so really there's sort of a disk in A in which we draw, anyway, then you extend that ball neighborhood, you use a 2-bit neighborhood of that ball, and to use you build a bump function using the radial direction out from the 2-bit neighborhood of that ball, and you do this isotopic that moves A up over there, and then damp it out by the collar neighborhood in that 2-bit neighborhood. I think that's, are you satisfied with that? Okay. It's not, that's not the hard part. Okay? It was all the dimension counting that was the hard part. And that's it. So maybe just a couple of comments about what happens in lower dimensions. We ended up, I think we really did actually prove it for any 6. And I think that there aren't any, I don't think there's any cases in which I was particularly sloppy. So what goes wrong in lower dimensions is that in lower dimensions, the basic problem is, well, there are several problems with getting, counting transverse intersections solved, but the basic problem is that Q may not be embedded. That last disk we were trying. By the way, that disk is often called a Whitney disk. And I have no idea what Whitney was way before the proof of the H-core isn't there, but for some reason they attached this. It's called a Whitney disk for the pair. So you got a pair of intersections, you're trying to eliminate them, and you find this disk that bounded by this loop. That's maybe Whitney was used. Well, that's sometimes called the Whitney trick to find that thing. I don't know it's too well enough. But so the Whitney disk may not be embedded, say, and so if we're looking at a 4-manifold, if we're looking at a 5-dimensional cobordism, and we've got a 4-manifold level set in which we're trying to embed this Whitney disk, it may have transverse self-intersections, okay? And then what you want to do is you want to say, well, those transverse self-intersections can pair off as well, right? And so you get something which is sort of, actually it's a little different. It's a little different. You draw a schematic that's sort of, this is supposed to be your cube, and this is the best you can do for sort of schematically. This is gamma here, right? That's your gamma, and this is your embedded, your disks transversely self-intersecting. And so then you want to actually, you don't have 2 points of intersection now. You just want to eliminate a single point of intersection. So you say, let me take my single point of self-intersection and take a loop in Q that goes around there, and then repeat. Okay, and of course you should expect, then that's all. Again, you're in a simply connected manifold, so that abounds some embedded disk, right? And well, the in a nutshell, which I don't understand, what Mike Friedman was able to do to prove the 4-dimensional topological point Gray conjecture was to say, if you want to kill the 2 points of intersection, you build this sort of tower of self-intersecting things. They intersect lots, right? So you'll see pictures like this or actually exist on papers. You build this weird tower of things, and then the non-smoothness occurs because you take a limit of this process. And in the limit of this process, you claim that this whole thing produces for you a topologically embedded disk, but not smoothly embedded disk. And that's obviously pretty hard to try to imagine how you do all that. It's not just it's a topologically embedded disk. I think showing it's a topologically embedded disk might not be so hard, but you want to show it's a topologically embedded disk with a topologically embedded collar neighborhood. So it's actually a topologically embedded handle. It's a topologically embedded disk cross disk of D2 cross D2, I guess, right? And then so thickening this in a proper way is probably the trickiest thing. Once you've got that, then you can topologically eliminate those two critical points. Don't ask me anymore. Okay? That's, topological four-dimensional. Topological four manifolds are something I'm very far from an expert. So, oh, and the other thing to say is if you're in some case where you have non-trivial fundamental group, you can still sort of do this around loops that are, if you find trivial loops, you can do this. And every time you sort of want to, if you say this gamma is originally a trivial loop, there's something to do with the lower central series. Like you take the fundamental group of your four manifold, and if you take the subgroup of commutators and commutators and commutators and commutators and commutators and commutators, you sort of build these towers in this way, and there's a whole technology related to understanding. These towers this tower may dead end at some point because you really don't get trivial. You eventually don't get a trivial loop, and that tells you something about sort of the structure of the group in terms of subgroups, of commutator subgroups, and so on all the way down. But that's all. So what I want to do now, I decided that I'm going to do circle A Morse theory next. So this is just a 3-minute introduction, and I actually got a book about it. It seems pretty good. I'm trying to learn. So this is partly because I want to learn this better. So anyone who wants to look at this is welcome. This is the library's copy. Welcome to look at it for me. Although my goal is to do the argument for you and read it and tell you about it. So you may not want to read it, but you're welcome to have a look at it in the office. But I'll start with sort of just the idea. We want to. Really focus on. We're going to have a function f now from the manifold to the circle. And it's going to be locally Morse. So all this thing about existence of Morse functions, all that goes through just fine. And because that's all really local instructions. And so that just means that as you go around the circle, right, you'll see critical points. You can sort of build up a handle decomposition where you take some regular level sets for the circle, and sitting over a point, you'll have some n-1 dimensional manifold as long as it's a regular value, and then you sort of go around and you attach handles, and then you glue things, and then whatever, you eventually get back to something that's diffeomorphic to what you started with, and then you glue it back somehow. So that's sort of the topological picture. It's not that hard, but already you should realize that even if there are no critical points at all, you can have an interesting manifold because you can take an n-1 manifold and glue it to itself by a non-trivial diffeomorphism and get interesting manifolds. So even in the absolute, any mapping torus, right, it basically gives a circulating Morse function with no critical points. So even in the absence of critical points, you have interesting topology, right? But we sort of want to focus on the part of the topology that does come from the critical points at first, anyway. And so you can set up a Morse. So what we're going to do is try and set up a complex, chain complex. And now the algebra is going to get kind of interesting because we've got some number of critical points, right? And suppose I have a critical point here of index. So we just need to pick a direction. I'm going the wrong way around the circle as usual. Kind of clockwise. So that's the up direction, right? So suppose that here I have a critical point in index k, and down here I have a critical point in index k minus 1. Of course, I can still make a descending manifold and count flow lines, right? Or I can take an ascending manifold here and descending manifold there and count intersections. But the thing to remember is that this descending manifold is going to keep going and it gets shredded as it runs into other manifolds, but some remnant of it will come back around, right? And could hit this k minus 1 critical point a second time. Okay, so you can have flow lines that go once, twice, 3 times around, right? And so if you want to, we can make a chain complex generated by the critical points, as usual. But what about the boundary now? Well, now the subtlety is that the boundary of critical point P is going to be, could in some sense be infinite, right? It's going to count, it's going to be the sum over all critical points of index k minus 1 times the number of flow lines, right? But there could be infinitely many flow lines in principle going around. So what you want to do is figure out a way to package that infinity, and what you want to say is that you're going to count, you're going to include in it how many times it's gone around. So you're going to say it's the sum over all critical points of index k minus 1, and now I'm going to write n sub pq times q, but now n sub pq is not going to be an integer. N sub pq is going to be n sub pq is going to be a polynomial in t. So we introduce a random variable called t, but it's, and I need to check for the exact notation, but I'm going to use a bracket. It's not just an arbitrary polynomial, it's still infinite, but what we want to do is say that this is equal to infinite polynomial, infinite degree well, what I really want, it's a infinite Laurent polynomial. Laurent means
Negatives as well.
arbitrary negative exponents, but it has a maximal positive, it has a maximal degree, but doesn't necessarily have a negative degree. So t is going to correspond. So if I have 25 flow lines from here to there, right? T is going to count how many times those flow lines cross this middle level, say. Okay, but with a negative direction because we're going downhill, right? So this would be, say, t to the 0 or something. I'll set this up more carefully. But the idea is that every time if you click past you get another t to the minus 1 in your count. Okay, so in principle, so these are infinite Laurent polynomials, but finite in the positive direction.
But how can you get something higher than degree?
Well, you don't get it right away there, but when you start, the thing is you're going to do everything as a module over that ring. Okay, so now in principle you might have t cubed times k as an element, or as an element. I mean, so this is going to be a ring of such semi-infinite Laurent polynomials. Okay, and now we have
but no,
particular
arbitrary products of them.
Right, I can take p. I can take p to the 5th minus t to the minus 1 times p, and what's the boundary of that, right? And that then can have positive. It should be linear over that, right? Times the boundary of p, right? And the boundary p now it's true that the boundary p itself is only going to have negative exponents or 0, but then once we start multiplying its coefficients, that's where I want to start next time. It does relate to the Alexander polynomial.